So this is section 4.3 in calculus. And today we're going to talk about some of the applications of integration, even though it'll take a little bit for us to actually connect it to integration. So first, let's think about something. Look at number one. Suppose I tell you want to estimate the area under this curve, and I've given you the equation right here of the curve. I want to estimate the area under that curve down to the x-axis on the interval from 0 to 4. So from 0 all the way to 4, I want to estimate all of this area. Now, it's not a specific figure that I have an area formula for. Like, that's not a rectangle, so I could do base times height. That's not a circle where I could do pi r squared. It's not a triangle. So because I don't have a specific area formula for that shape, we have to just estimate. And so what we're going to do, the way we're going to estimate is, it says, using 4 inscribed rectangles, so we want to make 4 rectangles within that whole area, whose height, meaning the height of each rectangle, is determined by the left side of each subinterval. Okay, so let's say if I'm going from 0 to 4, if I divide it into 4 equal intervals, right, then each interval is 1 unit wide. And it says, I want each of these to be a rectangle, but the rectangle's height is determined by the left side of the interval. So if you look at the interval from 0 to 1, the left side is right here at 0. And if I use that to determine the height, then this would be the rectangle I'm trying to find the area of. And if I look at that rectangle, it is going to be a base of 1 and a height of 1, right? So the area would be base times height, 1 times 1, okay? Plus, let's go to the next rectangle. Again, if I'm using the left side, so I'm looking between 1 and 2, the left side is right here when x equals 1, and the height of that rectangle would be 2. So the next rectangle is a base of 1 times a height of 2. And if I go to the next rectangle, the height is determined by the left side, which is somewhere here in the middle. And so this is the rectangle I'm trying to find. I don't want to just estimate that height. I want to know the exact height because I'm trying to get this area, even though overall it's an estimate, but I want each individual rectangle to be exact, even though all the rectangles together are not the exact area of the whole region that we're looking for. So how do I find the height? Well, I know the base is 1. Well, wouldn't the height be determined by x equals 2? In fact, if I were to put x equals 2 into the equation, wouldn't that tell me where it hits the curve? And so if I put a 2 into that equation, I'm going to get y to be the square root of 2 plus 1. So the height of that green rectangle is the square root of 2 plus 1. And let's go to the last rectangle. So if the left side determines the height, there's the height. So this one is still a base of 1, and this time the height is determined by x equals 3. And if I plug 3 into the curve, I'm going to get square root of 3 plus 1. So there are 4 rectangles represented here that I'm showing that I'm adding up. And I know I could use my calculator to add all this up and get a specific answer, but if this is on an AP exam, yes, you could use your calculator to do that, but we'd rather not because you don't want to take any chances of making a mistake. And on the AP exam, they will certainly accept an unsimplified answer. And there will be questions like this on the AP exam where they want you to estimate the area. Now, I want to point out up here in the equation, when you use the left side of the rectangles, that's called a left-hand Riemann sum. Riemann sum just means you're adding up rectangles. Left hand means you're using the left side of each rectangle to determine the height. Okay, well, look at number 2. What if we'd use the exact same curve, but this time we're going to do a right-hand Riemann sum? So in other words, the directions say I still want to go from 0 to 4. I still want 4 separate intervals. But this time, if I use the right side to determine the height, well, the first rectangle, the right side is right there at x equals 1. So that rectangle would be a 1 by 2. And then the next rectangle, if I use the right side, that's going to be the height. So this one is going to be 1 by, okay, again, the height was determined right here at 2, so that would be the square root of 2 plus 1 for the height. And then the third rectangle, if I use the right side, that height is determined by x equals 3. So it's going to be 1 by square root of 3 plus 1. And then for the final rectangle, if I use the right side to determine the height, that one's based on x equals 4, which actually comes out evenly to be a 1 by 3. Okay, so this is my area using the right side to determine the height. Now, if you look at these pictures, you can tell just by looking at what we've drawn. The first one, the left-hand Riemann sum, and by the way, let's just use notation for left-hand Riemann sum of LRS, left-hand Riemann sum. Notice that the area of the rectangles is actually less than the actual area I'm looking for. But on number 2, the right-hand Riemann sum, that one is a little bit too much, right? Those rectangles go over the actual curve. So on number 3, it says, let's write an inequality for the area. And so this A of x is going to mean the exact area using the information above. Well, we know that the exact area is going to be somewhere between the left-hand Riemann sum and the right-hand Riemann sum, right? The left is too low, the right is too high. Now, first question I have here is, will that inequality always be true? Will the left-hand Riemann sum always be too little and the right-hand Riemann sum always be too much, like it is in this case? Well, the answer is no. It depends on if the curve is increasing or decreasing. Notice on both of these, the curve was increasing. But if we were looking at a curve that were decreasing and we started separating that into intervals, in this case, the left side is going to be the higher one. And if I looked at the right side, same intervals, but if I looked at the right side, you see that one would be lower. So it all depends on if the curve is increasing or decreasing as to whether or not the left hand is smaller or the right hand is smaller. Okay, look at number 4. Estimate the area under the curve. All right, same curve. Still 0 to 4. Still 0 to 4. I still want 4 rectangles. But this time it says we want to use the midpoint to determine the height. So if I'm looking at that first interval from 0 to 1, the midpoint is going to be based on the middle there at 1/2. Go up and see where 1/2 hits the curve and let that be the height of the rectangle. So that first rectangle, now let's do this. Since each base is a 1, instead of putting 1 times, 1 times, 1 times, let's kind of put the 1 out in front for each of the 4 rectangles. And I get that you really, in this case, because they're 1, you don't have to write it. But it might be that each base is 2 or each base is 5. And so I'm just trying to show you it's okay if you factor it out. Okay. So I'm going to factor out the base of each one, which is 1, because it's 1 all the way across. So all I have to really do is add up the heights. And that first height is based on an x value of 1/2. So the height of that curve is going to be the square root of 0.5 plus 1. So there's my first height. Plus my second height is going to be based on the value at 1.5 right there. So the height of that rectangle is going to be the square root of 1.5 plus 1. And then the third rectangle is going to be based on the height at 2.5. So that one is going to be a height of the square root of 2.5 plus 1. And then the fourth rectangle is based on a height of 3.5. So whatever the height is at 3.5 plus 1. And again, if I were to add all that up on my calculator, that would give me my midpoint sum, meaning it's an estimate based on the midpoint. And in this case, it seems like the midpoint is a much better estimate. Sometimes it is, sometimes it's not. Now, I do want to stop and point out, on the AP exam, they want to see, I know this looks like a lot of tedium. Like I know that up here on number one, I know you could have done that in your head and gotten one. And you could have done that in your head and gotten two. And you didn't have to write one times. You could have just written that whole square root of 2 plus 1. I realize that. But on the AP exam, they want to see the base times the height for every individual rectangle. And if they don't see it written out like that, you're going to lose one of the points. Okay? So go down to number 5. Do you think the area represented by the midpoints is more or less accurate? Well, we already said in this particular case, it seemed like it was more accurate, but that doesn't mean it's always more accurate. How could you use the techniques described above to find a more accurate estimate of the area? Well, if you're using rectangles, to me, if you had more rectangles, like if I were in the same interval from 0 to 4, but what if I used 8 rectangles instead of 4? Do you see how I could kind of fill in the gaps a little bit more? Or what if I use 16 rectangles? Or in fact, the more rectangles you can have, the more accurate that area is going to be. Now, this is kind of a clunky way of writing it, but actually this is a limit. We could say the actual area would be the limit. Now, what kind of a limit? Well, I want more rectangles. How many more? As many as I can get. In fact, I want an infinite number of rectangles. So if my number of rectangles goes to infinity, okay, I want an infinite number of rectangles. Now, what am I doing with those rectangles? Well, I'm adding up all of the individual rectangle areas. So the notation for adding something up is sigma. I'm going to add up. What am I adding? All of the individual rectangle areas. Well, what's the area of a rectangle? It's going to be base times height. So this is just kind of a strange notation to say, hey, if I could get as many possible rectangles as possible, if I could add up all the areas, that would give me the exact area. Okay, let's leave that aside for a minute. Let's look at number 7. Estimate the area under the curve. Okay, it doesn't say it, but this is the exact same equation. But this time I don't want to use rectangles. I want to use trapezoids. Okay, we'll call this the trapezoidal sum. Now, I do expect you, and the AP exam expects you to know how to find the area of a trapezoid. So you may need to remember back from your geometry days, the area of a trapezoid is 1/2 times the height times the sum of the bases. And keep in mind, the bases are the parallel sides. Probably in geometry, most of the trapezoids you looked at were something like this, where the parallel sides were like the top and the bottom. But it doesn't have to be that way. In fact, if you were to take this and set it up on end like this, okay, the trapezoid might look like that. And that's how all the trapezoids are going to look that we're going to use. So look at number 7. I still want to go from 0 to 4. And I want 4 intervals. But this time, I don't want rectangles. I want trapezoids. So if I connect the top of each interval, those are 4 trapezoids. So keep in mind, in that first interval, this is a parallel side and this is the other parallel side. So those are my B1 and B2, meaning when x equals 0 and when x equals 1. So let's do this. Since every trapezoid is going to have a 1/2, and every trapezoid is going to have a height, and on these trapezoids, the height is going to be this base down here. I know you're like, well, that's the base, but because we set it up on end, that's the piece that's actually the height. So every one of these trapezoids is going to have a height of 1. And so now for each individual trapezoid, I could just add up the sum of the bases. So if the first trapezoid, the 2 bases are going to be at x equals 0 and x equals 1. And so the height of those is 1 plus 2. That's my B1 plus B2 for the first trapezoid. Let's go to the second trapezoid. The B1 and the B2 there are going to be 2 plus, well, what's this height right here when x equals 2? Well, it's the square root of 2 plus 1, isn't it? I guess I don't really need those parentheses, do I? Okay. Plus, let's go to the third trapezoid. So the third trapezoid is going to have this one and this one. So the first is going to be square root of 2 plus 1. And then when x equals 3, that height is going to be square root of 3 plus 1. So all of that is for the third trapezoid. And then the final trapezoid has these two sides. So that's going to be the square root of 3 plus 1. Oh, I needed more space. Why didn't I create more space, you guys? We can make this work. Okay, and then the second base is going to be right here, the square root of 4 plus 1, but I can tell right there that's just 3. So this is me adding up all 4 trapezoids. Okay, on the AP exam, they will always tell you how they want you to do the estimate. They'll tell you if they want you to use rectangles or if they want you to use trapezoids. And if it's rectangles, they'll tell you whether or not you should use the left side or the right side or the midpoint to determine the height. They will give you all that information. Okay, so on all of these, on 1 through 7, we did all this estimating based on the equation of the curve. Well, maybe they don't give you the equation of the curve. Maybe they give you a table of values for the curve. And probably this is a little more common on pre-response, that they'll give you a table of values. Okay, so it says, consider the curve f of x with these particular ordered pairs. Letter A, estimate the area under the curve. So I don't know exactly what the curve looks like. I just have a few ordered pairs. Estimate the area under the curve using a right-hand Riemann sum. So we're going to use the right sides of the rectangles. And it says I want 3 intervals, and I want those intervals to be of equal length or equal width, however you want to look at it. My suggestion is don't try to plot all those points. Let's just use the numbers we need, okay? So I know here's my x-axis. I know I'm going from 0 to 6. They said I want 3 intervals that are equal. So doesn't that mean each interval has to be 2 units wide? Okay, so each of these are going to be kind of the separators, for my rectangles. And I want to use the right side to determine the height. So from 0 to 2, I'm going to use the height at 2. Well, the height at 2 is 11. So the height of this rectangle is 11. So this rectangle is a 2 by 11. Okay. The second rectangle has, I'm going to use the 4 value to determine the height. And at 4, I know the y value is only 2. Now, again, it doesn't have to be drawn to scale. I'm just kind of estimating-ish. So the second rectangle is going to be a 2 by 2. Again, I know you guys could easily write in 22 and write in 4, but they want to see the multiplication of the base times height. And then the final one from 4 to 6, if I'm using the right side, I'm going to use the x equals 6, and the height at 6 is 6. So that rectangle is going to be a 2 by 6. So what they want you to write down, even though I know the person grading this could look at your picture, but graders are not supposed to read pictures, so you still need to write down area equals 2 times 11 plus 2 times 2 plus 2 times 6. Now, if you want to go on and say equals 38, great. But if you make a mistake in your addition, you're going to lose a point. So the way this would be graded is they would give you 1 point for the setup, 1 point for the answer. But if you never actually put the answer, if you just only put this, then that is counted as the setup and the answer, because remember, on the AP exam, you don't have to simplify. So they would automatically give you the second point with that. Okay, letter B, estimate the area under the curve. So we're using the same table. This time we're using a midpoint Riemann sum. But again, it says I still want 3 equal intervals. All right, well, like we said, we're going from 0 to 6, because that's what the table does. If I have 3 equal intervals, they're still going to each be 2 units wide. But I'm going to use the midpoint to determine the height. So on my first interval from 0 to 2, the midpoint would be x equals 1. And at x equals 1, I have a height of 8. So that rectangle is going to be a height of 8. So that's a 2 by 8. And then the midpoint between 2 and 4 is x equals 3. Well, the height at 3 is 4. So that's going to be a 2 by 4. And the midpoint between 4 and 6 is 5. And that's a height of 1. So that rectangle is going to be a 2 by 1. So my area is 2 times 8 plus 2 times 4 plus 2 times 1. Okay, and yes, usually this is going to be a letter A of a free response. And if the numbers are any uglier than this, it would be a calculator problem. But again, who cares if it's a calculator problem, because you don't have to do the math. You just have to show the setup. Okay, look at letter C. Estimate the area under the curve using a trapezoid. Again, though, we want 3 intervals, so 0 to 6. I want them to be equal intervals. They're not always equal. They will tell you if they have to be equal. In this case, they say equal. Okay, so for a trapezoid, I need to know both sides, right? So I know at 0, it was a height of 5. And at 2, it was a height of 11. So there's the first trapezoid. So that's going to be 1/2 times the base times the height, which is 2, right? That's the bottom. And then the sum of the bases would be 5 plus 11. How about if I do this? I'll say this is trapezoid 1. This is fine if I kind of label things. Okay, and then for my second one, at 4, my height is 2. So this trapezoid is going to be, I'll call this trapezoid 2, 1/2 times the height, which is 2. That's the bottom side. The sum of the bases is going to be 11 plus 2. And then for my third trapezoid, I'm going from 4 to 6. And let's see, at 6, we had a height of 6. So that's that trapezoid. So that's going to be 1/2 times the height, which is down at the bottom. And then the sum of the bases is 2 plus 6. And so make sure you show that you're adding these up. And I know it sounds dumb, but if you just leave it like that, you will not get full credit. You have to show that you're adding these up. Okay, so how about if I do this? I'll put the 1/2 out in front and the 2 out in front. And then the first trapezoid was the 5 plus 11. And the second trapezoid was the 11 plus 2. And the third trapezoid was the 2 plus 6. Now, did I have to add up to get the 16 and the 13 and the 8? No, I didn't have to. But it was fine to do that. It was just easier to write since I had already shown the addition up above. Okay. Let's look at the next page. All right, so let's bring it all into what does this have to do with integration? Well, I'm glad you asked. So integrals represent area. Okay, the synonym for integrals, as far as we're concerned, is going to be area. The entire first semester of calculus, we talked about derivatives, and if we had to define derivatives in one word, we would have said slope, okay? Same thing for integrals. If we have to define it in one word, we're going to say area. Integrals represent area. However, notice I didn't say integrals equal area, because integrals can give a positive or a negative value depending on whether the curve lies above or below the x-axis. Now, we're not saying the area is negative. It's just that the negative shows that the curve was below the x-axis. The area that you accumulated was actually below the x-axis. Now, I want to talk about something else that I haven't mentioned yet, this idea of a definite integral. We've never called them definite integrals. The reason we're going to now start calling them definite integrals is because when I set up my integral symbol, whatever I might be integrating, let's say I'm integrating f of x, now I'm going to give it definite boundaries. And so I'm going to say the integral from a to b. And those are just specific x values. So it might be the integral from 0 to 2 or the integral from 5 to 7. And the reason we have to give it boundaries is so that we know the beginning and ending of our area. Now, let me show you what I was talking about with this whole positive and negative business. Think about the graph of the sine function. Okay, the sine starts at 0. It goes up to 1. It comes back down. Then it goes down to -1, and it comes back to the x-axis at 2 pi, right? And let's see, right here in the middle, it was pi, and we said it started at 0. So this area would be represented by the integral from 0 to pi of the sine graph. Okay, that integral represents that area. If I were to put this in my calculator, and we're not going to talk about how to actually do this yet, we will later. If I were to actually put that in my calculator, that integral from 0 to pi of the sine of x, that would give me some positive value that would be equivalent to that amount of area. Okay, but if I were to think about this area that's below the x-axis, well, that would be represented by the integral from pi to 2 pi. So those boundaries are the beginning and ending of your region. I'm still integrating the sine function because the curve is still the sine function. But if you were to put that into your calculator, it would give you a negative value. It's the correct value. It's just going to say that it's negative because it's below the x-axis. Okay? All right. So look at example 1. It says, set up a definite integral that yields the area of the given region. So I'm not asking you what the actual area is. I'm just saying, what would the integral representation be? Well, I would say it's the integral from a to b is the beginning and the end of the region. Whoops, that's not a 2, that's a 3. So it would be the integral from -2 to 3. Now, what is that curve? Remember, f of x is the equation of this curve that you're looking at the area underneath. Well, that equation is the absolute value of x. And remember, integrals always end in dx. Okay, what about the second one? Well, I know it's going to be the integral from -3 to 3. -3 to 3. Be careful on this, though, because you're going to be tempted to say pi r squared because you're like, oh, the area of a circle is pi r squared, or in this case, a semicircle, 1/2 pi r squared. But remember, the integral does not have an area formula inside. Like over here, this absolute value of x, that's not an area formula. That's the equation of the curve. So on this second one, I need to know what's the equation of this semicircle. Well, wouldn't that equation be the square root of r squared minus x squared? Okay, so if I were going to type in this integral into my calculator, it would give me that area. Now, ironically, in this case, I don't need to, if I wanted to know that area, I don't need to look at it as an integral because I do know that the area of a semicircle is 1/2 pi r squared. So I know that's going to come out to be 4.5 pi. And if I put that integral in my calculator, it would be equivalent to 4.5 pi. Okay, right now we're talking about integral representations. All right, so look at example 2. Sketch the region whose area is given by the definite integral. Well, I'm not asking for the value, I'm asking for the picture. Well, what's the curve that's represented? Well, it's 2x plus 5. That is your f of x. So what does that look like? Isn't that just a line, mx plus b? So here's the y-intercept. I know I'm going to have a slope of 2. All right, so I want the area that's between x equals 0 and x equals 2. That's the area that's represented by that curve, by that integral. Okay, look at letter B. I want the area between 0 and 2 pi of the sine function. Well, that's the one we did up above. Remember the sine function, it takes 2 pi. Okay, that's kind of a sorry sine function, but it takes 2 pi to get one full section. And so the area is going to be that. Now, if I were to type this into my calculator as is, if I don't separate, if I were to type that into my calculator, can you imagine what the answer would come out to be? Hopefully, the answer would actually come out to be 0. Why? Because it took this positive value and this exact same negative value, and they said, oh, that's 0. That's why you got to be careful. Integrals are not equivalent to area. They represent area. So you have to be careful of what part's above and what part's below. Okay? So let's talk about some properties. These are just kind of some basic rules that we know about integrals. Well, the first one is the integral from a to a. Well, think about it. If the boundaries are the same, then there's no area, right? That's like up here saying on letter B, if I want to look at the integral from 0 to 0 of the sine function. So that would mean saying, hey, start right here at 0 and go to 0. Well, there's no area there. Okay, so hopefully that makes sense to you. So if the boundaries are the same, the answer is 0. Okay. The integral from a to b, if you want to, you can pull a negative out in front, which sounds strange, I know, but that would be the same as the integral from b to a of f of x. It's just a notation kind of thing. So like, for example, I could say, oh, the integral from 0 to pi of sine of x is equivalent to negative of the integral from pi to 0. So the standard way we would write it is to always go from low to high. But if you somehow end up with an integral where it's the other way around, it's like you have the high number on the bottom and the low number on the top, you can always switch those if you put a negative out in front. Just some little notation things that you can do. Okay, letter C, I'm going to adjust this. Instead of using the A to B, I'm going to say the integral from 0 to 10. It's just easier to see it if you have specific numbers. If you want, you can separate that interval into multiple intervals that you're going to add up. Like you might say that it would equal the interval from 0 to 3 of the function plus the integral from 3 to 10 of the function. So it's okay to separate it into multiple ones and do a section at a time. Kind of like when we were looking at that sine function, you could think of it as the integral from 0 to pi plus the integral from pi to 2 pi. Okay, when would you want to do that? Oh, you'll see. We'll get into some examples later where all of these little ins and outs are going to come in handy. Okay, letter D. Letter D is one that we've kind of already talked about. Remember how we said if you have a constant in your integral, if you want to, you can bring the constant out in front. If you want to, you could write that constant out in front, and then you could still look at it as the integral from a to b of f of x. We were doing this back when we were doing regular old integration. Okay, so look at example 3. And you will see, maybe a multiple choice, kind of this basic, like this example. So it says, I'm given the integral from 0 to 5 and also the integral from 5 to 7. Well, I can tell you right now, see how this interval is right next to this interval? So I'm going to think to myself, if I needed this, I'm going to write the addition problem. I could say the integral from 0 to 5 of this function plus the integral from 5 to 7 of this function is equivalent to the total from 0 to 7. Does that make sense? So letter A, what's the value of the integral from 0 to 7? Well, based on this equation, let's see, I said this part was 10, this part was 3, so wouldn't the total be 13? Okay, what about letter B? Well, oh, look, it's backwards of this one, right? So it's just going to be negative 10. What about letter C? Oh, look, the boundaries are the same, so that's just going to be 0. And then letter D, well, you got to think of this as 3, because you're moving the constant out in front, times the integral from 0 to 5. Hey, look, but don't we know that from 0 to 5 actually equals 10? So this would be 3 times 10. Okay, so just some basic things that you can do, some properties that you can do with integrals. So the homework there starts on page 205.